product of sums simplification. Use sum of product simplification on the zeros of the function in the K map to get F complement. So up to now we have seen how to represent sum of products, but if you want to represent that is max terms, okay, then you have to represent them with zeros, okay, and the resultant expression that we get is F complement. Find the complement of F complement, that is F complement whole complement equals to F, okay. So what we have to do is we have to go with taking the duality as well as complementing each literal, or we have to use the De Morgan's theorem. Let us take an example. How to generate a product term of sums from a K map. Use duality of Boolean algebra or as De Morgan law. Look at zeros in the map instead of ones. Up to now we have gone with the groupings of ones, but from now we have to go with the groupings of zeros for finding out the max terms, okay. And generate blocks around zeros, which will gives us inverse of a function. Use duality to generate product of sums. These are the three steps which we have to follow for realizing an expression or for reducing the expression, okay. So take an example here, one particular function, okay, and here this is plotted on the K map, and I've got, or this will gives us the F complement, which is nothing but AB plus CD plus BD complement, okay. And then you have to use the duality concept. So what is the duality concept? So the AND symbols are replaced with OR symbols, okay, so and zeros are replaced with ones. So if you can see here, AND symbols are replaced with OR symbols, okay, as there are no constants, so they are not replaced, and then we have to complement the function. So I have complemented the function, therefore I got this kind of expression. Let us see in detail with one more example. Before that, have two functions here, okay. One is sum of products and the other one is product of sums, okay. So as we have three minterms, okay, as we have three minterms here, so these minterms are realized with the help of AND gates. So I have took three AND gates here, and the outputs of these three AND gates should be summed, therefore I have took one OR gate, okay. And here we have three sum terms, therefore in order to get the sum terms we have to use OR gate, okay, and these are the inputs to the OR gates, and all these three sum terms are given as an input to the AND gate. Why? Because it is a product of sums. Now this is what how to minimize the POS, that is product of sums. So we have to only group zeros but not the ones. We have to consider only the zeros, which are nothing but max terms, okay. So I have gone with three groupings here, or three blocks. Two block size is 4 and one block size is 1, okay. So if you consider this particular block, okay, here the value of A is constant, which is nothing but 1. The value of A is constant, which is nothing but 1, and the value of B is also constant, which is 0, okay. But so therefore here we get A, B bar, okay. And if you consider this particular block, here the value of A is constant again, which is 1, and the value of B is varying, okay. And if you consider here, the value of C is constant, which is 0, but whereas the value of D is varying, okay. So the expression would be A, C bar plus, as I told you that if you are going with only one cell, okay, a group of one cell, therefore you will be getting 4 literals, that is A complement, B, C and D complement, okay. Why? Because here throughout this particular row the value of A and B are constant, and throughout this particular column the value of C and D are constant, okay. So we have got F complement. Now we have got F complement. Now we have to find the duality of this particular function, okay. So how to find the duality? So replace all ANDs with OR and ORs with AND, okay. So if you replace all those things, then you get this kind of expression, and then complement the function Therefore f complement whole complement is nothing but this is what the expression that we are going to get. And this is what 5 variable map. So 5 variable is nothing but how many combinations? It is 32 combinations. Okay, so therefore we'll get 32 minterms. As you can see, M0 to M15 will be occupying one map, and the remaining minterms, that is M16 to M31, will be occupying one more 4 variable map. So we are representing this 5 variable K map with the help of 4 variable maps. Okay, now here the value of A is constant throughout this map, which is 0, and BC on one side and DE on the other side. Here throughout this map the value of A is 1, which is constant, but whereas BC on one side and the other side is DE. Okay, now here these cells are, that is 0, 16, 1, 17, okay, 8, 24, okay, all these cells are called as adjacent cells. Okay, if you can see the value of this particular cell, that is A bar, B bar, C bar, D bar, E bar, if you consider this, then the value of this particular cell is A, B bar, C bar, D bar, E bar. Therefore only one literal is changing. Therefore these two cells are considered as adjacent cells. Now let us see the relationship between the adjacent squares and the number of literals. Okay, so here the number of adjacent squares, that is 2 power k. If k is 1, that is if a number of adjacent cells, if there is only one adjacent cell, then you will get the number of literals, that is if you are going with 2 variable map, then the number of literals would be 2. Okay, if the adjacent cells are 2, then inside the 2 variable map the number of literals that you get in the resultant expression is 1. Okay, and if the adjacent cells are 4, then you will be getting 0 literals, the output would be 1. So in the same way you can go with n equals 3, 4, 5, where n is the that is n, which is n is nothing but the number of variables. Now don't care conditions. There may be a combination of input values which will never occur. If they do occur, the output is of no concern. So in some cases we'll find some circuits where the output is not defined for some input combinations. Okay, so those outputs are called as don't care outputs. The function value for such combinations is called don't care. They are usually denoted with x. So all those don't care outputs are represented with x. Each x may be arbitrarily assigned the value 0 or 1 in an implementation. So we doesn't know whether the value of that particular x would be either 0 or else 1, and don't cares can be used to further simplify a function. So let us see how we are going to use these don't cares for reducing the function. Minimization using don't cares. Treat don't cares as if they are ones to generate PIs. Okay, so we have to treat the don't cares as ones for generating the prime implicants, or zeros while generating the prime implicants for the maxterms. Delete PIs that cover only don't care minterms. Okay, if you are forming a group which has only don't cares, then we have to delete that particular PI, that is prime implicant. Okay, treat the covering of remaining don't care minterms as optional in the selection process. So if you are going with some grouping, if any of the don't cares are remained or left over, so we have to ignore them. Let us see how to do that. So this is what the expression which has these minterms, okay, and these are the don't care terms. Now we have to plot all these minterms as well as these don't care terms on the map. So I have plotted, that is 0, which is represented with x, 2 it is again represented with x, and then 5 it is again represented with x. So as I told you that we have to go with maximum sized grouping, therefore I have gone with maximum sized grouping. So here we'll be getting yz plus w bar x bar. Okay, I can also group in this fashion where I'm going to use this particular don't care. Okay, but the result is same, which is nothing but I'm going to get only 2 minterms in the expression. Okay, so we are reducing an expression with the help of these don't care minterms. Okay, if we are not using these don't care minterms, then we would have got only one block whose size is 4 and the other block size would be 2. Okay, another example, simplify the function g of a comma b comma c comma d whose k-map is shown at right side. Okay, so this is what the k-map, already we have plotted it. Okay, now again we can go with the groupings in 2 ways. Have gone with in these 2 ways, where again you can see we have got only 2 minterms in the realized function or realized expression. Okay, fine, thank you. In the next session we'll discuss about universal gates and its advantages. Thank you.